Hello, everybody. My name is Raphael. I'm a PhD student from the Johannes Kepler University in Linz, Austria, and I'm really happy to share some of my work with you all. It seems like my talk is a bit of a follow-up talk to Francois' keynote, so maybe I can take some of the questions asked regarding machine learning after my talk then. So I will be talking about improving compiler optimizations by employing machine learning. And as it has already been topic today, I want to get a common understanding of the term compiler heuristic, as I will be using the term quite frequently. So compiler heuristics are metrics essentially to decide which transformation or optimization to apply in what way. So for example, when to apply loop peeling or what loop unrolling factor to use, stuff like that. For example, if you take a look at this code snippet here, what are we doing? We are comparing some code size delta with a weight, and we compare this with a performance delta with some weight. And depending on that comparison, we do then a transformation or not. So for example, we could evaluate the potential impact of a loop peeling transformation. And if the expected performance outweighs the code size increase, we will do that transformation. So in this code snippet, which could be present in your compiler as well, we can see several heuristics at several points. So of course, the weights are typically human designed and define some kind of heuristics which guide the transformation process, but also the whole idea of putting the code size and the performance into one context is also some kind of artificial heuristic to design or to guide the compilation process. So typically in state-of-the-art compilers, we have some hopefully very smart compiler experts who come up with such heuristics and deploy them or employ them in the compiler. Then those heuristics are executed on a set of benchmarks, which typically has to be reasonable small to be feasible to be analyzed by compiler experts. And depending on the results of the heuristics performance on when executed in the benchmarks, the compiler experts then update the existing heuristics. And this is a kind of iterative process where after some period of time, the compiler hopefully performs very well on the underlying benchmarks and hopefully also on programs in the real world. So basically, this approach, this state-of-the-art approach, requires a lot of domain expertise. We also have some kind of abstraction because we can only look at a feasibly large amount of benchmark programs. So we have to condense all the real world programs in some few benchmarks. So quite an abstraction is going on here. The compiler heuristics are often very static or one size fits all. So if they fit the benchmarks, they are shipped to all the customers. The customers might have very different needs depending, the use cases. For example, some long-running server application might use different heuristics and apply optimizations in a very different fashion than some often executed but short-running applications. Of course, this process requires a lot of manual maintenance and also updates. And as it is human guided, it is to some extent also error prone, of course. So this is a very experience driven approach as it is present in a lot of state-of-the-art compilers. On the other side, machine learning has found its way also into compiler construction some 20, 30 or more years ago. There are several approaches in how to improve compiler heuristics or compiler optimizations in general by using machine learning techniques. A very general approach is depicted here. So we try to describe our programs using some set of features, for example, the number of branches, number of memory operations, number of ifs or stuff like that. We define a target we want to optimize or we want to predict depending on the machine learning task. For example, the best loop unrolling factor or something like that. And we stuffed it into a machine learning black box and it spits out some heuristics which achieve the best performance for our training data. And we hope to be able to generalize on all the other data as well using our machine learning model. Another approach would be to directly have our machine learning models in the compiler. So the workflow for this would look like that. We got ourselves a compiler, are then able to compile a lot of different programs. So we are not restricted to some few benchmark applications. We can also compile specific user programs, for example, and in general are able to run way more applications and gather way more data. And we use this approach to produce features, descriptions of our functions, of our loops, depending on what we want to optimize. And using this data, we can train the machine learning model, which is deployed in the compiler and then does the decision-making process right in there. So this approach seems somehow automated, but it also reminds us a bit of the waterfall model in software engineering. So if the feature set changes, for example, or the target changes, we have to run everything all over again and start from the very beginning. So, but machine learning in compilers has some advantages and disadvantages compared to the traditional compiler expert-driven approach. First of all, we can capture a way larger amount of the real world. We are very data-driven in this whole approach. It is also at least semi-automated, although we have this kind of waterfall-y thing in there. But the disadvantage, and this was also mentioned in the keynote today, the disadvantage is that we might have a lot of black boxes in our compilers or do not know how or where our heuristics come from and why they are the way they are, basically. So we create a lack in maintainability and understandability by using a lot of machine learning black boxes, and it is really hard to infer further compiler knowledge when having black boxes everywhere in the compiler. And basically we're doing compiler research and we want to infer further knowledge. And this is a major drawback, I think. And of course, when using machine learning prediction directly in the compiler, and if you want to use the prediction online, so in a JIT compiler, for example, where compile time really matters, then this is most of the time also a big drawback, because machine learning models are most of the time, when invoked for prediction, not as fast as some simpler human-crafted heuristic having some thresholds and some if-else in there, and that's the end. So, but in general, this approach is very data-driven with its advantages and disadvantages. What we wanted to do is to combine the best of both worlds, basically. So we wanted, on the one side, from the human-crafted heuristic side, the maintainability, the understandability. We want to know what is going on in the compiler. And we also wanted to have this iterative style of being able to tweak around for some heuristics, leave others as they are, and not start all over again by invoking a machine learning pipeline from scratch. But on the other side, we wanted to have this data-driven approach by not being restricted to some few small benchmark applications for tweaking our heuristics to. We wanted to have this semi-automatedness from the machine learning approach as well. And so we aimed on combining those two approaches and hopefully gain some performance and understandability out from this approach. So let me show you how we propose this combined approach. So we still got our compiler experts in place who are responsible for designing the heuristics, updating the heuristics so they still know what is going on in the compiler. So nothing goes without a compiler expert giving the go. The heuristics are again implemented in a compiler, but then the machine learning pipeline comes into play, where we compile a lot of different programs, which can be either benchmark programs or can be tied to some user-specific domain, for example. And we use this approach to produce a lot of features, a lot of performance metrics for evaluation, for example, and we use this to train machine learning model. And now the machine learning model has two tasks. The first one is to assist the compiler in tasks which are not crucial for understandability. So only for some minor tasks where it is not that relevant if there is a small black box in there or not. And the more important part, though, is to support the compiler expert by verifying and fixing the existing heuristics in order to improve the whole system. So we want to avoid black boxes in parts which are crucial for understandability. We want to have this automated feedback based on environmental changes. So using this approach, we can check if the programs executed or programs compiled with our compiler have changed over the time. We can check using machine learning whether the model which was initially trained or the data which was initially used for manually creating the compiler heuristics still fit the newly incoming data. And the compiler expert can be warned and, for example, informed with, there has been arrived some new data, new programs are compiled, they do not fit the programs which were used for creating the heuristics. You might want to adapt your heuristics to fit those programs. And we want to use this approach to infer knowledge explicitly for the compiler experts. So for problem analysis, for example, when the machine learning model can tell the compiler expert, for this and that code pattern, I would do something different. Don't you want to check out your heuristics if they cover that special case or maybe could be improved on that part, for example. And this could also help us to compensate a lack of experience for some compiler experts and to gain some further knowledge. So we call this approach more data guided. We conducted a case study in the Graal VM on the Graal compiler where we applied this approach and tried to improve an existing heuristic in the Graal compiler for duplication. Duplication, in case you might not be familiar, is an enabling optimization. So duplication itself does not do much, but when conducted correctly, it enables further optimizations, as I will be showing on a small example here. So we have this if-else construct and a return afterwards, which uses a value which is assigned in the if and the else branch. And duplication now copies code after control flow merges. So we got this merge of control flow after the if-else and before the return. And we copy code after the control flow merge upwards into the predecessor blocks. At this point, it, of course, increases the overall code size and has not much use yet. But when done correctly, we can then enable further optimizations. So in this case, we can apply some constant folding and get rid of some assignments and performance, as well as the code size performance increases, and the code size actually decreases for this example. But when duplication is executed prematurely, we get a huge increase in code size in general. So what we wanted to do, we wanted to take a look at how duplication is performed in the Graal compiler. And actually there are a lot of heuristics, human crafted heuristics in there to trigger duplication. So to put it simple, in the Graal compiler, the human crafted heuristic estimates the code size impact of a duplication and also estimates the performance gain of the duplication. And if the performance gain outperforms, let's say, the code size increase, then we duplicate and otherwise not. The Graal compiler does this estimations by using the Graal intermediate representation, which is a graph representation of the program. And in this graph, for each of the compiler IR nodes, an abstract size is assigned to this node, as shown in the example on the right. So we got a Graal graph here. The red edges are the control flow edges. The black upward edges are the data edges. And we can see for each node which will have an impact on the final code size, there is an abstract size assigned, and the same is done with an estimation of the performance impact of a node. Basically, there are 450-ish different IR nodes in Graal, and the model in the compiler has a handwritten label for each of those nodes, including the size, impact, and the execution cycles. And those are values created by compiler experts with a lot of experience, but they are only estimations of the real impact. So what we wanted to do is we wanted to learn the actual code size impact per IR node based on a lot of data. And we wanted to use a machine learning model for this. So as features for this model, we just used the number of different nodes in the R graph. So the number of add nodes, the number of if nodes. So we also had some structural information in there, and so on and so forth. And for those node counts of a graph, of a function to be compiled, we wanted to learn then the actual code size. Instead of having to predict an abstract code size impact, we try to directly predict the code size in bytes of the final program. So the input for our machine learning model simplified looks like this on the bottom right. So a lot of different compilations where we measured the final code size, and also during duplication, the number of nodes of the graph for our predictive model. While it seems like a linear regression kind model, there arose quite a big problem when taking a look at the abstract depiction of the compiler here, where a lot of different compiler phases are executed one after another. Duplication is just one phase in the very middle. And we take our features from at a point of duplication, basically, and we want to predict the code size after all the compiler phases were executed and the code is turned into machine code. But as you can see here, there are a lot of influencing compiler phases which change the graph and also the number of nodes of a particular type after duplication. And thus, this problem to some extent wrecked our linear relation between the nodes and the final code size. We experimented initially with a very simple linear regression model, but this model mispredicted a lot, let's put it like that. And thus we required a nonlinear predictor to account for those influencing compiler phases being in the compiler after duplication. So we decided to take out the big guns and trained an A&M predictor on our problem, a very simple A&M predictor. So just 2 or 3 hidden layers with 50 to 100 nodes each. And we used our predictor, we trained our predictor on some benchmark suits, some well-known benchmark suits. And on the right here, you can see some condensed results of our predictor. So the x-axis shows the relative error of the predicted code size versus the actual code size of the outputted code at the very end. So basically, we can say 3 out of 4 predictions had errors with less than 10%. And we implemented a prototype predictor in the Graal compiler to do these size predictions in the duplication phase. And as we wanted to gain knowledge on the existing model for estimating the code size, we implemented an analysis mode in Graal which compared the outputs from the machine learning model versus the human crafted model, and also measured or stored whether the duplication decisions would differ based on the differences in the code size estimation or prediction. So we provided a lot of output for some interesting code patterns, alongside with information about the structure, the nodes, and the type of function to the compiler expert, in order to be able to find some bugs and misclassifications in the existing human-crafted model. And actually, we were able to find some problems in the existing and deployed model. So apart from some minor bugs, we found some misclassifications in this human-crafted model. For example, I've picked some interesting looking benchmarks here. You can take a look at jet stream towers, for example, or containers. We can see that the green parts are the default implementation of Graal. For some cases, we found that it is crucial that, or it was crucial that the existing model underestimated the code size impact severely, and we found that this was because return nodes and loop ends were labeled with a too small abstract code size. And this resulted in a very liberal way of applying duplication. And as you can see here, we got some 15% code size bloat for the towers benchmark, which even resulted in some throughput decrease. And also for Jetstream, we had some overhead here. And the purple parts are the machine learning model approach, basically. And the orange part is then the one where compiler experts fixed the issues which were shown by the machine learning prediction and pointed out by the machine learning model, and fixed those misclassifications and bugs in the existing human-crafted heuristics. And as we can see here, for especially for the Jetstream container and towers benchmark, some big improvements regarding code size were achieved. And sometime later, we were reported by the Sulong guys that for some benchmarks after our merge, even 10 to 12% performance increase was reported. So what I want to give as a message is that while machine learning might not be a panacea for every kind of problem, because it has problems with decreasing understandability and maintainability, it can be used together with expert knowledge to create further knowledge on problems which might be overlooked by simple domain expertise driven approaches. And for stuff like that, machine learning can be really helpful as long as it does not take over everything in the compiler and we do not understand what is going on anymore. And with this, I say thank you and are open for questions.
I have a question. So the training data is very important for a model, right? So for instance, like if you have this set of benchmarks, it could work well for this set of benchmarks, but do you see it working well with, like, if you take like a regular application, does it perform better there as well? Or does it become very specific to the benchmarks that you are training it for?
Of course, the training data really matters. We picked a problem where I guess we have some good generalizability. So for some particular optimizations, when letting a machine learning model decide whether to apply particular optimizations or not, I think it would depend more on the training data which was used. But the problem of predicting the code size at the very end is, I think, not that much influenced by the training data. But in general, I would say we have to, in order to use machine learning, we have to take as much data as we can to cover all the possibilities and all the possible use cases. Or depending on the usage, we might want to use only a very small set of training data to train our model to fit that particular kind of data, which might be suitable for particular customers, which have particular kinds of applications and want to have a machine learning model tied to those applications. But in general, the more training data, the more versatile the training data, the better the overall generalizability. Yeah.
Thank you. We have a question from the chat as well. If you want to unmute yourself, Vaidas, and ask the question, or I can ask here. Okay, so the question is, do you know some other parts of software life cycle replaced or helped by ML AI?
So some other parts of software life cycle. So this is a very broad area, I'd say. But in general, I'd say every domain where a lot of data, analyzing a lot of data might provide further knowledge is an area where machine learning would perform well, I'd say. So of course, there are many areas in the software creating life cycle. But I think especially for performance analysis and stuff like that, where a lot of data has to be analyzed, I think machine learning will perform well.
Great. We have time for one more question. Peter, do you want to ask the question?
Yeah, okay. Thank you.
Thank you.
So thank you, Raphael. So the compiler expert was able to fix the bugs in the heuristic after seeing the difference between the ML model and the existing heuristic. So what if you didn't give him the ML model? What if you just provided the training data? So the actual sizes that you use, would that also help, or how is the ML model better in here?
So the ML model itself doesn't need to be provided to the compiler expert, I'd say, but the decisions the ML model has made compared to the decisions the human crafted heuristic has made is information that is relevant for the compiler expert. So we could, of course, through all the data we gathered at a compiler expert, but this would not lead to an easy and time efficient way of finding those problems. It was a big advantage that we were able to run a lot of benchmarks, and at the very end we had some 15, 20, 100 condensed outputs where some severe differences between those two models were found, and then the time could be used very efficiently to take a look at some particular patterns which were crucial for those mispredictions in the actual model. So from my point of view, the value lies with the output which is provided by the machine learning model and pointing the compiler expert in the right direction to not be in the need of analyzing manually thousands of data points, I'd say.
Okay, thank you.
Great. So thank you again, Raphael.
Thank you.